morning, everyone. Thank you for joining us today. We're diving deep into the intricate world of computer hardware once again. I'm excited to explore these critical topics, and as always, I'm joined by our expert guide, ready to illuminate the complexities.
Hello, everyone. Thank you for having me. It's a great pleasure to be here to discuss this important topic.
Great to have you. Last time we looked at interfacing with the machine, the I/O systems, how we actually interact with our computers. Today, we're shifting gears, really moving inwards to what gives the machine life, its fundamental support systems, power, and thermal management.
That's right. It's easy to focus on the flashy CPU or GPU, but without stable power and effective cooling, none of that performance matters.
Exactly. I like the analogy of a high-performance engine. It needs clean fuel constantly and a really good cooling system, otherwise it just seizes up.
Precisely. The same laws of physics apply inside your computer case. Immense power demands, immense heat generated. You have to manage both.
And the speed we're seeing now in processors and graphics cards, it's truly breathtaking. But it's all built on these, well, often overlooked foundations.
The power supply unit, the PSU, delivering that stable electrical energy, and then the cooling systems, handling the thermal load. They really are the unsung heroes of stability, longevity, and getting the performance you paid for.
So our mission today is to really dissect the modern PSU. We'll figure out how to calculate power needs correctly. We'll also explore the physics behind thermal management, which is pretty fascinating stuff.
And compare the different cooling technologies out there, air, liquid, all that.
Yeah, this is super relevant for, well, pretty much anyone using a computer seriously. Think about a video editor in Vancouver pushing their workstation hard.
Or a research lab in Waterloo running complex simulations. The principles are the same.
Absolutely. So this is going to be a comprehensive Q&A, really, for our tech audience, students, anyone enthusiastic about technology. Okay, let's unpack this then. First question. What is the fundamental role of the power supply unit, the PSU, in a computer system?
Okay, so the PSU, you could call it the energy hub. Its main job, its primary function, is conversion. It takes the high voltage alternating current AC from your wall outlet.
The standard power we get at home.
Exactly. And it converts that into stable, low voltage, direct to current, or DC. That's the kind of power the delicate components inside your PC actually need.
And you mentioned stability. Why is that so critical?
Well, investing in a high-quality PSU is honestly one of the most important things you can do for your system's health, stability, and longevity. Because a failing PSU, or just a low-quality one delivering unstable power, it's not just an annoyance if your system crashes.
Right.
It can potentially damage everything connected to it. Motherboard, CPU, RAM, drives, everything.
Wow, okay, so it's a protector, but if it fails, it could be the cause of major damage.
Absolutely. It can be the single point of failure that takes out the whole system. You really don't want to skimp on the PSU.
That's a stark warning. So that leads perfectly into the next point, how they actually fit into a build. How do PSU form factors and modularity affect things?
Okay, form factors. These are basically standardized physical sizes and shapes. Just like with motherboards, they ensure that the PSU physically fits into different types of computer cases.
Like ATX. That's the common one for desktops, right?
Exactly. ATX is the dominant standard for most desktop builds. It dictates the physical dimensions, mounting points, and even the main power connector layouts. But if you're building a smaller system, say using a mini ITX motherboard for a compact build, you'll need a smaller form factor like SFX or SFXL.
Okay, so form factor is about physical compatibility. What about modularity?
Modularity is all about the cables. It refers to how the power cables connect to the PSU itself. And this actually has a big impact.
How so?
Well, it affects how easy the computer is to build, sure. But maybe more importantly, it impacts airflow inside the case. You have three main types. Non-modular is the cheapest. All the cables are permanently attached to the PSU body.
So you end up with a bunch of unused cables just sitting there.
Pretty much a big bundle you have to tuck away somewhere, and that can definitely obstruct airflow, trap heat.
Right. Then what's next?
Semi-modular. This is a popular middle ground. The essential cables, like the main 24-pin for the motherboard and the CPU power cable, are fixed. But the other cables for graphics cards, SATA drives, peripherals, are detachable. You only plug in what you need.
So better airflow than non-modular, easier cable management.
Yep, balances cost and convenience pretty well.
And the third type?
Fully modular. Maximum flexibility. Every single cable is detachable, including the main motherboard and CPU ones. This lets you achieve the absolute cleanest build, route cables precisely, and get the best possible airflow.
But I guess it costs more.
It does, yeah. It's usually the premium option, often preferred by enthusiasts building high-end systems or those who really value aesthetics and optimal airflow.
Makes sense. So modularity isn't just cosmetic, it can actually help with cooling by improving airflow.
Directly impacts it, yes.
Okay, moving on to another label you see on PSUs, the 80 plus certification. What does that actually signify?
Ah, the 80 plus rating. This is
Yeah.
really important for understanding PSU quality. It's a voluntary certification program focused on energy efficiency.
Efficiency, meaning how much power gets wasted.
Exactly. See, no PSU converts AC to DC perfectly. Some energy is always lost in the conversion process, and it's lost primarily as waste heat. An 80 plus certified PSU guarantees a minimum level of efficiency at different load levels, specifically 20%, 50%, and 100% of its rated wattage. The baseline is 80% efficiency.
But there are different levels, right? Bronze, silver, gold.
Correct. The tiers go up in efficiency. 80
Yep.
plus, standard, then bronze, silver, gold, platinum, and the highest is titanium. A titanium unit might be, say, 94% or 96% efficient at certain loads, meaning it wastes very little energy as heat. A bronze unit might be more like 82, 85% efficient.
So why pay more for higher efficiency, just saving electricity?
Well, saving electricity is part of it, sure, over the long term. But the bigger immediate benefit, especially for system stability and cooling, is that a more efficient PSU dumps less waste heat into your computer case.
Ah, so it makes the cooling job easier for the rest of the system.
Precisely. Less heat from the PSU means the internal ambient temperature stays lower, which helps keep your CPU, GPU, and everything else cooler.
So what level do you recommend generally?
For most builders, balancing price and performance, an 80-plus bronze or gold-certified PSU from a reputable brand is usually the sweet spot. Titanium is great, but often the price premium is quite high unless you need absolute peak efficiency.
Got it. Bronze or gold for the win, usually. Now let's talk wattage. Choosing the right power capacity seems absolutely vital. How do you figure out how much wattage you actually need?
This is critical, yes. Get it wrong and you'll have problems. Too little power and underpowered PSU leads to instability, random shutdowns, crashes, especially when your components are working hard, like during gaming or rendering.
And too much power.
Too much isn't dangerous, but it's wasted money. You're paying for capacity you'll never use, and PSUs are often less efficient at very low load levels relative to their max capacity.
Okay, so how do you calculate the right amount?
The wattage rating on the PSU tells you the maximum total power it can deliver across all its rails. To estimate your needs, you need to look at your components. The two biggest power consumers, by far, are the CPU and the graphics card, the GPU. You need to find out their power draw figures.
Where do you find those?
Manufacturer spec sheets are the best place. They'll often list a TDP or a maximum board power. You need those numbers. A good rule of thumb is to add the maximum power draw of your specific CPU model and your specific GPU model together.
Okay, CPU plus GPU.
Then add roughly 100 to 150 watts on top of that. This accounts for everything else, the motherboard itself, your RAM sticks, SSDs, hard drives, case fans, any RGB lighting, all that other stuff.
Right, so CPU plus GPU plus maybe 150 watts, is that the final number?
Not quite. That gives you your estimated peak system draw. You should then choose a PSU that offers about 20% to 30% more wattage than that total.
Why the extra headroom?
Two main reasons. First, components can sometimes have brief power spikes that exceed their typical max draw. The headroom covers that. Second, PSUs are generally most efficient and run coolest when operating around 50–70% of their maximum rated load. Running a PSU constantly near its 100% limit stresses it, makes it run hotter, less efficiently, and can shorten its lifespan. That headroom keeps it in a happier, more efficient operating range.
That makes sense. So calculate peak draw, then add 20–30%.
Yep. And if you want a more precise estimate, there are some really good online PSU calculator tools. You can plug in all your specific components, and they'll give you a recommended wattage.
Very useful. Okay, beyond just the total wattage, you mentioned rails earlier. Can we dig into that? What are voltage rails, and why is the plus 12V rail so important?
Right, the rails. So a PSU doesn't just output one voltage. It provides power at several different DC voltages needed by different parts of the computer. These separate voltage outputs are called rails. The three main ones you'll always see are plus 12 volts, plus 12V, plus 5 volts, plus 5V, and plus 3.3 volts, plus 3.3V.
And you're saying the plus 12V is the most critical?
Oh, by a huge margin in any modern system. The plus 12V rail is responsible for powering the hungriest components. We're talking the CPU.
Through that extra connector near the top of the motherboard.
Exactly. The 8-pin EPS connector, usually. And crucially, the graphics card or cards through those 6-pin or 8-pin PCIe power connectors. These two components consume the vast majority of power in a high-performance PC.
So when looking at a PSU specs, the rating for the plus 12 VRail is key.
Absolutely the most critical spec. You need to ensure the PSU can deliver enough amperage and therefore wattage, specifically on that plus 12V rail to handle your CPU and GPU combined load. You might also see some higher-end PSUs mentioning multiple plus 12V rails.
What's the deal with that?
It's a design choice. Instead of one massive plus 12V rail, they split it into several smaller ones, each with its own overcurrent protection limit. The idea is potentially better load distribution and maybe faster tripping of protection circuits if one specific output has a problem. Though single high amperage plus 12V rails are also very common and work perfectly well.
Okay, so plus 12V does the heavy lifting, but the others are still needed, right? What do the plus 5V and plus 3.3V rails do?
Definitely still needed. While plus 12V handles the big power draws, the system wouldn't run without the others. The plus 5V rail typically powers lower power components. Think M.2 drives, SATA drives. Both SSDs and older hard drives get some power from plus 5V, and importantly, many USB devices draw their power from the plus 5V rail.
Ah, okay. USB power comes from plus 5V.
Largely, yes, and the plus 3.3V rail. Its role has diminished a bit over time, but it's still essential. It's used primarily for some of the chips directly on the motherboard, like certain chipsets or controllers. It's also used, along with plus 5V and sometimes plus 12V, by SATA and M.2 storage devices.
So even though they handle less power overall, they're still vital.
Absolutely, and this ties back to PSU quality. A good PSU doesn't just deliver enough watts. It delivers stable, clean power on all these rails. That means minimal voltage fluctuation, known as ripple, and minimal electrical noise. Clean power is crucial for the stability and, again, the longevity of all those sensitive electronic components.
That's a great point. It's not just quantity, but quality of power.
Precisely.
Okay, let's shift gears now. We've talked about delivering power, but power usage inevitably creates heat. What's the primary source of heat in a PC, and why is it dangerous?
Heat is the unavoidable byproduct of electricity doing work. Any component with current flowing through it generates heat. It's a fundamental principle called joule heating. In a computer, the undisputed champions of heat generation are the CPU and the GPU.
Why them specifically?
Because they contain billions, literally billions of microscopic transistors. And these transistors are switching states on and off billions of times every second to perform calculations. Each tiny switch generates a minuscule amount of heat, but multiply that by billions of transistors switching billions of times per second.
And the heat adds up incredibly quickly.
Enormously quickly. High-end CPUs and GPUs can easily generate 100, 200, even 300 watts or more of thermal energy, all concentrated in a tiny piece of silicon, maybe the size of your thumbnail.
Wow. And if that heat isn't removed?
The temperature skyrockets. Modern components have built-in safety mechanisms. The main one is thermal throttling.
You mentioned that earlier. What exactly is it?
It's a self-preservation technique. When the chip's temperature hits a predefined safe limit, it automatically reduces its operating frequency, its clock speed, and sometimes its voltage. This reduces its power consumption and therefore its heat output, allowing it to cool down or at least stop getting hotter.
So the direct consequence of inadequate cooling is lower performance.
Absolutely. Your CPU or GPU simply cannot sustain its maximum boost speeds if the cooling can't keep up. You paid for high performance, but you won't get it if it's constantly throttling due to heat.
And in a worst-case scenario, total cooling failure.
Extreme cases, yeah. The system might perform an emergency shutdown to prevent damage. Or, if protection fails or the heat rises too rapid, you could potentially cause permanent physical damage to the chip. Heat is the enemy.
Okay, so managing this heat is paramount. How do we actually combat it? What are the basic physical principles behind computer cooling?
The core goal is simple. Move heat energy away from that small hot source, the CPU or GPU die, and dissipate it into the much larger volume of ambient air, usually outside the computer case. This movement of heat relies on a few key physics principles. The first is conduction.
Heat moving through solids.
Exactly. Heat travels through solid materials. Think of the heat moving from the silicon die itself into the metal base of a cooler. Good thermal conductivity in the materials is key here. The second principle is convection. This is heat transfer involving a moving fluid in our case. That fluid is usually air, but it can also be liquid coolant.
Like air moving over heatsink fins?
Precisely. The moving air or liquid picks up heat from the surface and carries it away. This is why fans are so crucial in most cooling setups. There's also radiation, where heat is emitted as electromagnetic waves. It plays a role, but in most standard PC cooling, conduction and convection are the dominant mechanisms we engineer around.
So the effectiveness of any cooler depends on how well it uses conduction and convection.
Fundamentally, yes. How efficiently it can conduct heat away from the source and then convect it into the surrounding air or liquid.
Right, and the most common application of these principles we see is standard air cooling. How does a typical air cooler actually work on a CPU?
Or cooling is definitely the mainstay. It's generally reliable, cost-effective, and performs well for a wide range of components. A standard air cooler has two main parts, a heat sink and a fan.
The block of metal with fins?
That's the heat sink. Usually it has a base made of copper because copper is excellent at conducting heat, which makes direct contact with the CPU, with thermal paste in between, of course. Attached to this base are many thin fins, typically made of aluminum. These fins dramatically increase the surface area available for heat dissipation.
So heat conducts from the CPU into the copper base and spreads out into all those aluminum fins.
Correct. Then you have the fan, which is mounted directly onto the fin stack. The fan's job is to actively blow cool air from inside the case across all those fins.
And the moving air picks up the heat.
Via convection. It absorbs the heat from the large surface area of the fins and carries that warm air away, ideally towards an exhaust fan that pushes it out of the case.
Simple concept, but clearly effective. Now, many higher performance air coolers use something called heat pipes. What are those and how do they help?
Heat pipes. They are a fantastic piece of passive thermal technology. They significantly boost the performance of air coolers. Essentially, a heat pipe is a sealed copper tube. Inside, there's a vacuum and a very small amount of a working fluid, usually water, that has a low boiling point.
How does that help move heat?
It's quite clever. The end of the heat pipe is embedded in the cooler's base, right above the CPU. As the CPU gets hot, it heats the liquid in the pipe. Because of the low pressure inside, the liquid boils and turns into vapor at a relatively low temperature.
Okay.
This hot vapor then travels rapidly up the pipe, away from the CPU, towards the cooler part of the pipe running through the aluminum fin stack. As the vapor reaches the cooler section, it condenses back into a liquid, releasing the latent heat it was carrying into the fins.
So it dumps the heat into the fins much more efficiently than just relying on the metal itself to conduct it all the way up.
Exactly. The phase change liquid to vapor and back to liquid is a highly efficient way to transfer thermal energy over a distance. The condensed liquid then flows back down to the hot end, usually via gravity or a wick structure inside the pipe, and the whole cycle repeats continuously.
That's brilliant, like a little passive engine moving heat.
It really is. Heat pipes allow air coolers to handle much higher heat loads than a simple solid block of metal of the same size could. They're fundamental to modern high-performance air cooling.
Okay, so air cooling with heat pipes is very capable. But for the absolute highest performance or for serious overclocking, people often turn to liquid cooling. How does that work?
Liquid cooling definitely offers superior thermal dissipation potential, which is why it's favored for really high-end CPUs and GPUs, especially when overclocking. The basic principle is actually quite similar to the cooling system in your car.
Radiator, pump, fluid, that kind of thing.
Pretty much, yeah. You start with a water block. This is a small, specialized heat sink, usually with a copper base, that mounts directly onto the CPU or GPU. Then you have a pump. Its job is to circulate a special coolant, typically distilled water, mixed with anti-corrosive and anti-biological additives through the system. The coolant flows through channels in the water block, absorbing heat directly from the component.
Okay, so the liquid picks up the heat, then where does it go?
The heated liquid is then pumped through tubes to a radiator. The radiator looks a lot like a car's radiator. It's a large heat exchanger made of metal with lots of thin fins to maximize surface area.
And fans are involved too.
Yes, fans are mounted onto the radiator. They blow cool ambient air across the radiator's fins. This transfers the heat from the liquid coolant flowing inside the radiator tubes into the air via convection again.
So the liquid gets cooled down in the radiator.
Right, and then the pump pushes the cooled liquid back through the tubes to the water block to pick up more heat, restarting the cycle. It's a continuous loop moving heat away from the component and desiccating it via the radiator.
That sounds effective. Now, within liquid cooling, I know there are different approaches. What's the difference between an AIO, an all-in-one cooler, and a custom loop?
Good question. That's a key distinction. They both use the same principles, but the implementation is very different. All-in-one, or AIO, coolers are what most people use when they opt for liquid cooling these days. They are pre-assembled, factory-sealed units. An AIO typically consists of the water block, often with a pump integrated into it, pre-attached tubing, and the radiator with fans, all connected and filled with coolant at the factory.
So basically plug-and-play liquid cooling.
Almost, yeah. Installation is generally much simpler than custom loops, often comparable to installing a large air cooler. They offer a big chunk of liquid cooling's performance benefits with much less complexity and no real maintenance needed as their sealed systems. That's why they're so popular.
Okay, and the alternative, custom loops.
Custom loops are the domain of serious enthusiasts, modders, and those seeking the absolute peak thermal performance or specific aesthetics. With a custom loop, you buy every component separately. The water block, or blocks if you're cooling the GPU too, the pump, a reservoir to hold extra coolant and help bleed air, the radiator, or multiple radiators, the tubing, either soft or rigid, and all the individual fittings to connect everything.
Yeah, sounds like a project.
It definitely is. You have to plan the loop layout, cut tubing, assemble everything carefully, fill it with coolant, and leak test it thoroughly. The payoff is potentially the best possible cooling performance, the ability to cool multiple components in one loop, and complete control over the look of your system. But it requires significant expertise, a much higher budget, and periodic maintenance, like flushing the loop and replacing the coolant.
Right, so AIOs for ease and good performance, custom loops for ultimate performance and customization, but with more effort and cost.
That's a good summary, yes.
Okay, one last key metric to unpack, and it's one that seems to cause a lot of confusion. TDP, thermal design power. What is it, and why is it often misunderstood?
TDP. Yes, this one trips people up all the time. It's arguably one of the most important specs related to cooling, but also one of the most frequently misinterpreted. So what TDP is, fundamentally, is a specification from the chip manufacturer, like Intel or AMD for CPUs or NVIDIA AMD for GPUs. It represents the maximum amount of heat, measured in watts, that the component is expected to generate under a typical sustained real-world workload.
Okay, maximum heat under typical load, so it's about heat output.
Exactly. It is primarily a measure of thermal output, intended to guide system builders and cooler manufacturers. It tells you how much heat your cooling solution needs to be able to dissipate effectively.
So what isn't it? Because that seems to be where the confusion lies.
Right. Crucially, TDP is not the absolute maximum electrical power the chip can draw. Modern CPUs and GPUs often have boost mechanisms where they can temporarily exceed their rated TDP for short bursts to achieve higher performance, drawing more power and generating more heat momentarily. It's also not a direct measure of the component's performance. A higher TDP generally correlates with higher performance potential because more power often means more speed, but it's not a performance benchmark itself.
So its main job is guiding cooler selection.
Precisely. The significance of TDP is that it tells you the minimum thermal dissipation capacity your cooler needs to have. If you buy a CPU with a 125W TDP, you absolutely need a cooler rated to handle at least 125W of heat.
And if you use an undersized cooler,
You guarantee poor performance. The chip will constantly hit its thermal limit and engage in thermal throttling, slowing itself down dramatically to avoid overheating. You won't get the performance you paid for. Matching your cooling solution's capability to the component's TDP is absolutely critical for stable, optimal performance.
that clarifies it a lot. It's a thermal spec for cooling design, not a power consumption or performance guarantee.
Exactly. Think of it as the heat load the cooler needs to be prepared to handle continuously.
Fantastic. We have covered a huge amount of ground today, from the volts and amps of the PSU to the thermodynamics of cooling. Let's try to bring it all together. To summarize, what are the key considerations for ensuring system stability through power and thermal management?
Okay, summing it up, the incredible performance we get from modern hardware really rests on these two pillars: stable power delivery and effective thermal management. They're the foundation. So, takeaway number one, the power supply unit. It's the silent, vital heart. Don't skimp on it. Choose a high-quality, efficient unit aiming for 80-plus bronze or gold is a good starting point. And crucially, calculate your wattage needs correctly. Factor in your CPU, your GPU, add wattage for everything else, and then add that 20–30% headroom. Getting the PSU right is step one for reliability.
Solid advice. And the second key area.
Thermal management. Those powerful components generate immense heat, and that heat is a constant enemy of performance and stability. You absolutely need a well-designed cooling system, whether it's a capable air cooler with heat pipes or a liquid cooling setup, AIO or custom, to dissipate that heat effectively. This allows your components to actually reach their full performance potential without constantly throttling back. And remember, TDP is your key guide here. Match your cooler's capability to the TDP of the components it needs to cool.
It really drives home that these aren't the parts to cut corners on if you want a system that performs well and lasts.
Absolutely. You could have the fastest processor in the world, but without stable power and adequate cooling.
It's just an expensive paperweight.
Or, as you said earlier, an inert, hot piece of sand.
Yeah.
Power and cooling are the bedrock.
What an insightful deep dive. We've really unpacked these often overlooked but absolutely critical components, from PSU form factors, modularity, and efficiency ratings like 80 plus, to understanding wattage needs, voltage rails, the dangers of heat, the physics of cooling, and comparing air, AIOs, and custom loops. And finally, demystifying TDP.
Hopefully, it gives everyone a much better handle on how crucial these elements are.
I think so. Understanding these principles really empowers anyone building or even just using a computer to ensure they get the stability and performance they expect. Looking ahead, next time we're going to explore another fascinating area: parallel processing and specialized accelerators. That sounds like another deep dive into cutting-edge tech.
It should be very interesting, yes. Lots happening in that space.
We can't wait. A huge thank you for sharing your expertise today. And thank you, everyone, for joining us on this deep dive. Please do subscribe to our channel, Tech, AI, and Beyond, so you don't miss future episodes and can continue exploring the amazing world of technology with us. We'll catch you on the next one.